Now that we've talked about combustion reactions, I want to talk about how we can calculate how much energy is released in a chemical reaction or absorbed. Um, but first, I want to review what we've learned about endothermic and exothermic reactions. So, breaking bonds absorbs energy. Breaking bonds is an endothermic process. Uh, Making bonds, on the other hand, releases energy. It's more energetically stable. It's what this explains why bonding happens is because you create a more energetically stable um, uh, format for the atoms, and so this process releases energy. So most reactions involve both bond making and bond breaking. So they're gaining some energy, they're losing some energy, and whichever process involves more energy determines whether the overall reaction is endothermic or exothermic. So endothermic reactions absorb more energy than they release. So there is more energy absorbed during breaking bonds than released during bond making. And in an exothermic reactions, those release more energy than they absorb. As a reminder, this calculation for an overall energy change in a reaction is called Q. The Q value is positive in an endothermic reaction and negative in an exothermic reaction. So, just kind of pictorially reminding you how what this looks like. This is an endothermic reaction pathway diagram, and we learned about these in Unit 1. So, in an endothermic reaction, heat enters the system increases in energy. So you can see at the end of the reaction here, this is at a higher energy level than we were at the start of the reaction. Because of that increase in energy, Q is positive. Notice that this value here, from the start to the finish, we went up, so Q is positive. Um, and remember, energy cannot be created or destroyed. So if the chemicals are increasing in energy, that energy had to come from somewhere, and that comes from absorbing heat from the surroundings. So the surroundings are decreasing in energy. Um, and this is why the surroundings feel cold. An endothermic reaction feels cold if you're holding the container kind of in your hands. It'll feel cold to the touch because that energy is being sucked in from the surroundings and kind of incorporated into the bonds of the products. On the other hand, for an exothermic reaction, heat is exiting the system, exiting the chemicals. So you can see here that the system decreases in energy. The reactants are at a higher energy level than the products. So the Q value is negative because this change from reactants to products has gone down. Heat cannot be created or destroyed. Energy in general cannot be created or destroyed. So that energy has to go somewhere and it exits the system as heat and goes into the surroundings. So the surroundings increase in energy, and that's why exothermic reactions feel hot. And so the quintessential example of this would be combustion reactions. Those feel hot. And so those are a good example of exothermic. So, if you want to calculate, use bond energy, overall Q values for a reaction, you can do this using bond energies. And here's the step-by-step procedure. First of all, you have to draw full covalent Lewis dot structures for all the reactants and all the products in the chemical reaction. We learned how to do this in Unit 2, but basically you're going to need to count each type of bond that you have, and so drawing the full covalent Lewis dot structure is helpful for helping you count those up. So you have to count the number of each type of bond in the reactant. So starting on the left side of the chemical equation, you need to also account for the coefficients in the balanced equation. And then you're going to add up the energies for all of those bonds that you've counted on the reactants side. Uh, Please note, I'll give you a table of bond values. but carbon-oxygen double bonds have different energies depending on what molecule they come from. And particularly carbon dioxide, since we're going to do most of our examples are going to be combustion reactions, that carbon oxygen double bond in carbon dioxide has an energy of 799 kilojoules per mole. It's in the bottom right corner of the table that we have. And I'll show you that on the next slide. But then all of that counting and adding that you did for the reactant side, you then have to do that for the product side. And then once you have the reactant's total bond energy and the product's total bond energy, you just subtract reactants minus products. Because reactants, remember, bond breaking is an endothermic process. So this is going to be a positive value. And by subtracting the products, we make that an exothermic process with that negative value. And so if more bonds have been broken, then you have more of a positive value and your overall Q is positive. Whereas a higher value of bonds have been made, have been formed, then overall your Q value would be negative. So overall you would have an exothermic reaction. So looking at this data table, that bottom right-hand corner gives you the carbon-oxygen double bond bond energy that you should use for carbon dioxide. Do not use this one here unless it's as part of a molecule that isn't carbon dioxide. These are average bond energies, so the specific bond energy does change depending on what particular molecule you're looking at, but on average, the bond making and bond breaking requires or releases this much energy. So let's look at one of these calculations, what one of these problems looks like. Calculate the energy change for combustion of methane. So here's a balanced chemical equation for the combustion of methane, which is CH4. It reacts with oxygen to form water and carbon dioxide. My first step is to draw full covalent Lewis dot structures to represent the methane, 2 molecules of oxygen, 2 molecules of water, and 1 molecule of carbon dioxide. So that's what this looks like. I have drawn 1 methane, 2 oxygens, 2 waters, 1 carbon dioxide. So now I can start counting things up. So on the reactant side, everything kind of above the line, I have 1, 2, 3, 4 carbon-hydrogen bonds. And if I look up on the data table that I showed you on the previous slide, 1 carbon-hydrogen bond has a bond energy of 413 kilojoules per mole. So I need to take that 413 and multiply by the 4 carbon-hydrogen bonds that I see here. And that total is 1,652 kilojoules per mole. Now I'm going to look at the oxygen. I see an oxygen-oxygen double bond here and an oxygen-oxygen double bond here. So I have 2 oxygen-oxygen double bonds. When I look that up on the data table that I showed you on the previous slide, you can see that an oxygen-oxygen double bond has a bond energy of 495 kilojoules per mole. I need to take that number and multiply by 2 to get 990 kilojoules. And now I'm done counting all of the bonds in the reactant side of the equation. So I just add those kilojoule values together and my total is 2,642 kilojoules. I'd like to point out a couple things here. First of all, notice that I kind of crossed out the bonds as I counted them. That way I can make sure that I've counted all of the bonds and I haven't lost track of anything. Another thing that I want you to notice is that I am counting a double bond is different to counting 2 single bonds. A double bond is a single entity, so you want to make sure when you're looking things up on the data table here that you are looking up an oxygen-oxygen double bond, not trying to do two separate single bonds. It won't work out correctly that way. Now let's progress on and do the same thing for the products. On the product side, I see that I have 4 oxygen-hydrogen single bonds, 1, 2 in that water molecule and 1, 2 in that water molecule. The oxygen-hydrogen single bond has a bond energy of 467 kilojoules per mole, so I need to multiply that by 4, and that gives me a total of 1,868. And then I have the carbon-oxygen single bond, carbon-oxygen double bond. I have 2 of those. And remember, this is inside carbon dioxide, so I do want to use that bottom, the value from the bottom right-hand corner of the table, which was 799 kilojoules per mole. So I take that 799, multiply by 2, and get 1,598. I've now counted all of the bonds here on the product side of the reaction. So I add those together and I get 3,466 kilojoules. Now that I've added all the reactants, added all the products, I just do reactants minus products. 2,642 minus 3,466 is negative 824 kilojoules. And that is an exothermic reaction. Because it is negative, it is exothermic, it's releasing heat to the surroundings. And this is a good check to make sure that you've done the calculations correctly, because this is a combustion reaction. I'm expecting it to be exothermic. And so just confirming that is an indication that I've hopefully done this correctly. Let's look at another example. Calculate the energy change for the combustion of propane. Propane is C3H8. It reacts with 5 molecules of oxygen to form 4 molecules of water and 3 molecules of carbon dioxide. So if I were to draw the Lewis dot structures for all of these substances, here's my propane molecule, C3, 3 carbons. Carbons are always in the middle of their covalent structures, and the hydrogens are arranged around the outside. 5 oxygen molecules, 4 waters, and 3 carbon dioxides. This is a more complicated example. There's more going on here and more to think about in terms of making sure you're counting all of the bonds required. So first of all, one new kind of bond that I see here are the carbon-carbon bonds. I see 2 carbon-carbon bonds, and each of those has a bond energy of 347. Then I have, I believe the next one I count is the hydrogens. So I should undo that previous one. I'll just come back to it later. 1, 2, 3, 4, 5, 6, 7, 8 carbon hydrogen single bonds. So 8 times 413 is 3,304. And now I can come over and cross out the oxygen-oxygen double bond. 1, 2, 3, 4, 5 of those oxygen-oxygen double bonds, which have an energy of 495. So I multiply that out and I get an answer of 2,475. And when I add those 3 values together, my total for the reactants is 6,473 kilojoules. If I look at the products now, I'll look at the water first. I've got 1, 2, 3, 4, 5, 6, 7, 8 oxygen hydrogen single bonds. 8 oxygen hydrogen single bonds each have a bond energy of 467, but when you multiply times 8, that's 3,736 kilojoules. And then when I count my carbon oxygen single bonds, 1, 2, 3, I said single bonds. I meant to say double bonds. 4, 5, 6. Then 6 oxygen carbon double bonds, each worth 799. But when I multiply by 6, that totals 4,794 kilojoules. And when I've added those values together, I have a total of 8,530 kilojoules. The final step is to do the subtraction problem, reactants minus products. So 6,473 minus 8,530 gives us negative 2,057 kilojoules. Again, this is a combustion reaction, so I'm expecting it to have a negative Q value to represent that exothermic change. I hope this helped.